All right. So we'll work through some more truth population stuff today. And at the end, if we have time, I'll go over some stuff that I hopefully will kind of clarify a little bit with what we're doing with hypothesis testing. So let's get going here. So last class, we looked at these examples where we were comparing two sample means. We had this assumed true difference, which for us, we said we're always going to use 0. And then we knew the population variances, right? So just like with one population examples, we also can look at proportions. So maybe we want to look at the difference between two population proportions, right? So we would have two groups, right? The first one will have its own sample size, and we could find the sample proportion for that group. We know the variance for that group would look like this, right? This was the exact same equation that we're using for one population, right? Now, usually we need the standard deviation, so usually we would see this and then we'd be taking the square root, but that was only because usually we want the standard deviation, but this would be our variance, right? We then have a second group. They have their own sample size, their own sample proportion. Their variance would look the exact same, but right, we're using the sample proportion and sample size from that group. Right? So then really all we're doing there is we've identified our sample size, sample proportion, and the variance of each one of these distributions. Well, just like with the sample means, when we look at the difference in sample proportions, that difference will be normally distributed, and it's going to be normally distributed, and I'll come back to this in a second, around whatever the true difference is in the population proportions, right? This is the exact same thing that we had for means, just now we're doing it for proportions. Okay? The variance of the difference in those proportions will just be add up the variance from each one of these. And I guess, if we had the true population proportions here, that's what we should be using. We don't have them, so we'll use kind of these estimates or these sample proportions that we find. We'll add the two variances for both groups together. That would give us the variance for the difference in the sample proportions. If we want the standard deviation, we just take the square root. Okay. So what we're looking at visually here be something like this. Right? So we want to know what the difference in these sample proportions are. They're going to be normally distributed around whatever the true difference is, right? And then kind of our standard deviation for the differences in those proportions. Well, we would just take the variance of each group. Right, we're gonna run out of room here, but we would do this for the second group as well. It's on the slides here. And now we would have the standard deviation of our distribution for the statistic we're interested in, which is now the difference in these sample proportions. And we now know the mean of this distribution for the statistic we're interested in as well. Okay. So if we think about what we're doing with confidence intervals, we're now gonna base our confidence interval around whatever the sample statistic we found was. Well, here now our statistic is the difference in our sample proportions. We're dealing with proportions, so we can still use that standard normal distribution. We'll want the z-value that gives us kind of alpha over 2 on each side of our confidence interval. And then here, we'll multiply by the standard deviation of the statistic we're looking at. So that's just the standard deviation of the differences in our sample proportions, which we know from the slides, or as I kind of had started up here, the square root of, and here I left myself enough room to completely write it out. I'll get out of the way here in just a second. All right. So it's going to be the same format we've been using. Oh, someone's trying to get in. Same format we've been using for all of our confidence intervals. It's just now we're doing this for the sample proportions, right? Like last class when we had the sample means, instead here we had, what did we have? We had, I can get this to right, there we go. Right, we were adding the variance of our sample means together and then taking the square root to get the standard deviation, but it's still like the same process, okay? Any questions on that? Shouldn't be too bad, just kind of a slightly different formula than what we were looking at last class. So this is kind of one of those things to make sure that the samples are large enough. I'll never have examples where this isn't true, so we don't have to worry about that, but just for completion. So here's our confidence interval equation. The steps to building this, I mean, really, you're given these two sample proportions in the problem. You're given the two sample sizes. It's just about plugging those values in and then knowing how you find the z value for whatever confidence level you want. That process looks no different than what we were doing with one population examples. So we still look up alpha over 2, find the z value that would give us alpha over 2 in the tails, plug that in, now we get everything we need. So if we're working through an example, oh, here we go, here's all the steps, but right, identify what you're given, find that z value, and then it's just a matter of plugging and chugging, right? So let's say I have an example like this. So surveys for 2011, 2010, we have whether or not people favored ensuring healthcare coverage for everyone, right? We have pretty large samples in both those years, 600 and 607, and we have our two sample proportions, 0.84 in 2011, 0.82 in 2010. What would the 99% confidence interval be between 2011 and 2010? So we're thinking about the difference between kind of the newest year and the oldest year. Anytime you're kind of looking at these change over time, always think about your group 1 is going to be the most recent year, and then kind of group 2 would be your older year, right? So here, what would our alpha be? 99% confidence interval, so alpha would be 0.01, right? So how much is on each side? 0.01 divided by 2, or 0.005, right? So we know our alpha, we have our two sample portions, our two sample sizes. Now we think about what is the difference that I'm going to find here. 0.84 minus 0.82. So my confidence interval should be centered around 0.02. So which of these can I rule out right away? One of them is very easy I can rule out. If I'm building my confidence interval around 0.02, that means it has to be smack dab in the middle. So is 0.02 even in this confidence interval? No. So right away, I know that can't be a possible answer. Right? If I check the other ones, it looks like 0.02 is in the middle of all of them, so that can't rule out anything else out, but we can for sure rule out C. Remember, we're building the confidence interval around our new statistic, which is, what is the difference, right? If that difference is 0.02, I know 0.02 should be smack dab in the middle of my confidence interval. Okay? All right. So from here, right, I've already mentioned the sample proportions, our sample sizes. We had our alpha. How do I find alpha over 2? Well, I'm going to actually cheat to get to the third decimal. I could go to the standard normal table, right? Find the area of what? 0.005. So right here. So negative 2.57 and negative 2.58. So 2.58. Or if I use the t-tables and I go all the way down to the very last row, remember these are the values to the third decimal from the standard normal distribution if I did have degrees of freedom of infinity. So I go up here, 0.005, 2.576 would be the value that I need, okay? So I can actually go out to the third decimal there if I use that student t-table. Once I have that, it's just a matter of plugging everything in, right? I've got my equations for the confidence interval, right? So it's just a matter of getting everything plugged in there. Okay? And like I said, if you're working on a calculator, sometimes to make this easier, kind of entering it into your calculator kind of from actually right to left might make it a little bit easier, okay? Or, you know, if you're comfortable with using parentheses and putting it all in at one time in your calculator, that's fine as well. So here we get this confidence interval from negative 0.03 to 0.07, right? So is this an interesting confidence interval? Well, I mean, with 99% confidence, I can't really say whether or not views have went up about, you know, healthcare coverage for everyone, or whether or not they've went down, because remember, this range is telling me with 99% confidence, one of the values in that range is the true population mean. Sorry, not true population mean. True difference in these proportions, right? Well, if the difference is negative, that would mean that 2011 views would be lower than 2010. If it's positive, that would mean 2011 would be higher than 2010. Well, I have, a range that goes across 0. It has some negative, some positive. So I can't really say whether or not it's went up or down with 99% confidence. In fact, one of the true possible values could be, so if I think about, I've got negative 0.036, 0.076, I think it was. One of the true possible values could be 0, which if the statistic I'm interested in is the difference in the sample proportions, that means one of the true values for that population, the difference in the population proportions, could be 0, which means they would be the exact same value. So it could very well be that from 2010 to 2011, the views remain the same. That's one of the possible values that it could be. Okay? Any questions on that before we keep moving? Shouldn't be too bad. All right, so let's look at a slightly different example here. And let's do at the same level of confidence, right? So I'm not going to go through the step of looking up the z-value here, because what should the z-value be? If we're looking at the 99% confidence interval, it's the exact same thing that we just found, right? It's going to be the same alpha. It's going to be the same alpha divided by 2. We're going to find the same value when we look it up in the table, right? It doesn't change. So now we're dealing with some slightly different sample proportions. And I think I'm using this more so to kind of, it's interesting to think about what we can do with these confidence intervals. So in 2011, it was 0.51. 2010, it was 0.48. Those are two sample proportions, but what are they talking about? Well, they were asking whether or not people had unfavorable views of the Affordable Health Care Act. So in 2011, 51% of people had unfavorable views of it, 48% people in 2010. Okay, so I'm still taking 2011 minus the 2010 value, right? So when I go, and I don't know, I just like that meme because it's, never mind. That's a whole nother issue. Anyways, so I've got sample proportions, sample sizes. I know what my alpha is. We said, well, look, we just did a problem where we found that z-value that would give us 0.01 divided by 2 or 0.005 in the tails. It's going to be the same value again. Now it's just a matter of plugging away, right? Excuse me. Get my sample proportions plugged in where they belong. Get my sample sizes plugged in where they belong. We've got that z-value. Now I get a confidence interval here of negative 0.04 to 0.1, right? So once again, can I really say anything about kind of the difference in the views on the Affordable Health Care Act over this time? Well, no, because some of the possible values are negative, and this got cut off a little bit. So here, so this looks a little, oh, I had it, never mind. I wrote it down here. Right, so negative 0.04 to about 0.1, right? Well, once again, with 99% confidence, I can't really say whether or not, the views of the Affordable Health Care Act went up or down, or they could have just been the same, right? Because one of the true possible values could be 0 in this range. Right? But what might be a little bit more interesting is to kind of think about looking at this. You could compare the proportion of people who had unfavorable views of the Affordable Health Care Act. Notice how low these proportions are. What was the first confidence interval we did? Was for whether or not same people supported healthcare coverage for everyone, which is one of the main, it's essentially what the Affordable Health Care Act was trying to do. And so if we looked at like the difference between people who actually really what they're saying is, I support the main part of the Affordable Health Care Act, but their views didn't reflect that, right? So that's another interesting kind of comparison of proportions you could do. Okay. Yeah.
How do you choose which value is P1 or P2?
So typically it'll be indicated for you on like a problem, but it really doesn't. It doesn't really matter. It's just going to matter in the way that you say it in English. Now, like I said, on an exam or something to make sure that you're not going to get the answer wrong, I'll usually like put in there like i.e., like what's the difference, i.e., and then like give you, so instead of like P1 and P2 here, the problem would read something like this, like i.e., the difference between the sample. So like it'll be kind of made sure that you know what it is. But it really doesn't matter because if I set it up this way, I'm going to find that the difference is somewhere between these two values. If I just flip-flop them, what I'm going to find is, what, negative 0.076 and 0.036. It's going to be the same values. It's just that they're going to be kind of flipped around, right? So it's like saying, let's see, think about it. If I think about the difference between 2011 and 2010, the sample evidence I found was 0.02, right? Well, if I said it working backwards, so how did the views, if I was going back in time, how did the views used to look? Well, they would have been 2 percentage points lower, or negative 0.02. So when we're dealing with these time examples, it really is always the newest time period minus the oldest, because that's how we say things, right? Have things increased or over time? Have they decreased over time? We don't say did things decrease if we look backwards in time? You know, it's just not the way that we typically do it. Now, if we have examples where I was thinking about the differences between opinions on the Affordable Health Care Act and healthcare coverage for everyone, well, there we need to be a little bit more careful. But yeah, on any problem, it'll be indicated kind of how you're doing that. Any other questions on that? I mean, it shouldn't be too tough. I think with these confidence intervals, it's like we have a few more moving parts, but it's really the same idea of what we're doing before, right? Now, the hypothesis testing gets a little bit more tricky. So hypothesis testing, we typically would think about, we have this variance on our sample proportions that we were using for the confidence intervals here, right? But now, because, how do I want to explain this? So with the confidence intervals, we were not assuming any true value, right? But by assuming that there is a true value for this difference, the distribution, right, or when we convert this into a test statistic, to make sure that it follows a standard normal distribution, we actually have to calculate the variance a little bit differently. Because if we had different sample sizes, right, it's going to affect the fact that we're using estimates for what the true population proportions are a little bit differently, right? So you can prove this to yourself in Excel, that if you use this equation, you'll get a slightly different answer than if you kind of approach it by simply adding up the two variances. But it kind of throws a wrinkle when we're going to calculate this test statistic. The fact that we need to use a slightly different equation to calculate the standard deviation for the differences in our sample proportions makes this denominator look quite a bit different than anything we've done before, okay? So I think the top part of this test statistic makes sense, right? What's the statistic we're interested in? The difference in our sample proportions. We'll then subtract some assumed true difference, which for us is always just going to be 0, right? Is this proportion greater than the other? Is it less than the other? Or is it not equal to the other? Kind of talked about that idea last class. But now to get the standard deviation of our sample proportions, we're going to have to first calculate this p-bar, right? I mean, we don't have to. I guess technically you could plug this equation in, but it makes that denominator like really hard to like use a calculator, you know, for. So we're first going to do this intermediate, step of finding p-bar. Once we have that value, we'll plug p-bar in, plug in our other information that was given to us, and be able to calculate the test statistic pretty easily. You know, it is a little bit more cumbersome, but that's what we have to do in order to make sure that this test statistic or this Z statistic actually is a Z statistic, that it actually is coming from a distribution where the mean is 0, variance is 1, okay? So we'll work through a problem to kind of see what this looks like with some values, right? So the steps are all the same, right? Nothing's changed. This is the same slide that we've been looking at. If we want to do the critical value approach, we use the type of test in alpha, find our critical values, figure out where our rejection region is, calculate our test statistic. Now is going to be a little bit different, right? Because we have a new test statistic equation, but all the other steps are identical, right? So I looked this up yesterday. I think the numbers changed a little bit today, but we'll go with what was going on yesterday. So this is a company that correctly predicted the election in 2016. Did another phone survey. They've been doing them like almost every day or every couple days, and they've got 1,500 likely voters. So these aren't necessarily registered voters, but they're people who responded they're likely to vote. Okay, so we don't know if they're registered or if they're not, but they're likely that they'll be registered and vote on the election day. So they found that 49% of people plan to vote for Biden, while 47% of people plan to vote for Trump. All right. If you look at some of the other polls, they're quite a bit wider. Like I said, this one I chose because it's kind of interesting to think about. If we did have a prediction that was a little bit closer, could we say that the true difference between these two is 0, right? Well, it's actually want to test something slightly different, not that just that if these are different, maybe I want to predict whether or not Biden will win. So I want to test the proposition that Biden will receive more votes than Trump. So really what I'm thinking about there, and before we think about this as a difference, if I want to know if Biden's going to get a higher proportion of the vote than Trump, and this is just to predict the popular vote, we're not trying to predict the outcome of the election necessarily. What I'm really saying is, what I want to test for is that population proportion for Biden greater than that of Trump, right? So if I rearrange that a little bit, what I'm really saying is the difference between Biden and Trump is that greater than 0, right? Because if he's going to get more votes, well, then the difference would have to be greater than 0. Or sorry, more votes. A higher proportion of the votes would have to be greater than 0, which means we're going to assume the opposite is true. And the way that we typically write this is that difference, our alternative is that it's greater than 0. We'll assume the opposite is true, right? And if we want to write this alternative hypothesis out, kind of using that indicator for what that difference is, we're saying, is that difference greater than 0? That's what we want to test for. We assume the opposite is true. But really, that is just another way of thinking about it. Kind of the way that we speak in English, we don't say, is the difference between, we say, is the proportion of votes Biden's going to get greater than that of Trump? Okay? And if it helps you to write out the alternative this way, and then kind of like rearrange so that you do have the difference in the proportions, and then you can kind of see, oh yeah, if I subtract this from this side, I'm just left with 0, then you can go ahead and do that, right? That helps. Okay. So what type of tailed test do we have here? So we look at the alternative hypothesis. We have a greater than sign, so we have a right tailed test, right? Greater than a right tailed test. Okay. So what we've assumed is that for this difference in our sample proportions that we found, we've assumed that it's 0. That was kind of our cutoff, right? So if we're thinking about what our distribution for that difference in our sample proportion should be, it should be centered around 0. Okay? We found, what was our sample evidence? I think it was 0.49 and 0.47. So the difference we found was 0.02, right? Which for a right-tailed test is good. That goes against our null. I shouldn't say it's good. It's interesting. It goes against our null, but does it go against our null enough that we can actually reject that null hypothesis? Kind of recalling that null was that the difference was greater than or equal to 0. No, not greater than or equal to 0, sorry. Less than or equal to 0. Okay. So what do we need to do? Well, we have a normal distribution. We want to turn that into a standard normal distribution so that we can get our z statistic or our test statistic. Once we have that, if we want to use the p-value approach, we want to find the area to the right of that. If we want to find the critical value approach, we would then go to that same standard normal distribution, but instead, we would want to find the critical value that would give us alpha in the tail, figure out our rejection region, and then plot our test statistic against it. Okay? So we don't have to do both, but we're going to. So the equation that we had, we first had to do that intermediate step, which is a little bit different than what we did before, which is, and I'll come back to the critical value in a second. Right? First, we have to calculate this p bar, right? So I plug in my sample proportions, I plug in my sample sizes, which were both the same because it was coming from the same survey there, 1,500 people, and we get this p-bar of 0.48, okay? So first, just plug in your sample proportions and your sample sizes into our p-bar equation. Now, into our test statistic equation, we have p-bar, we have our sample sizes, we have our sample proportions. The assumed true difference here was 0, so that just kind of goes away. And we get this test statistic of 1.097. Right? So we now know what our test statistic is. If I wanted to find my p-value, what do? I go to my table. Now I have to go to 2 decimals here, so if I round this, it's what, 1.10 if I round it to the second decimal here. So I'll go to my, oh, I didn't want to do that. I'll go to my standard normal distribution table. I'll go down to 1.10. The area to the left is 0.8643. Okay. So 0.8643 was the area to the left of that value. I wanted the area to the right, so 1 minus 0.8643 should be what? 0.1357. Okay. So if I wanted to be able to reject the null, even at an alpha of 0.1 or 10% significance level, or said differently, the 90% confidence level, could I reject, what this is really saying is that Biden is either going to get the same amount of votes or fewer than Trump. Can I reject it at that 10% significance level? No, I only reject if the p-value is less than alpha, right? So we only reject the p-value is less than alpha. 0.13, not less than 0.1. So with 90% confidence, we can't actually reject that the true difference could be negative or could be 0, or that Biden would be receiving fewer votes, right? We can't reject that. So it's possible that he loses the popular vote if we wanted to say that with 90% confidence. Now, I mean, yeah, we failed to reject that, but I mean, 0.13 is not that far away, right? I actually could reject that with 85% confidence, right? There, my p-value would be the same, but with 85% confidence, my alpha is 0.15. Now, it's not one of these benchmark values because we usually like to be able to say things with at least 90% confidence, but I mean, I don't know, being able to say it with 85 doesn't seem a wildly different to me. You know, it's not that far off. Let's not get too caught up on like always trying to hit this benchmark value. Like this is still evidence, fairly strong evidence that we could reject that null, or we could reject that the difference between the votes will be 0 or negative, which is really saying we've got evidence that Biden's going to have a higher amount of the popular vote, right? Well, with 85% confidence, but yeah. So, I mean, this is, I think, kind of interesting, at least pretty relevant, if nonetheless. So this is kind of our p-value approach, right? What if we want to do the critical value approach? Well, hopefully we'll come up with the same scenario. But here, I'm going to give you a little bit more room so we can see this. So let's say, I'm going to keep switching colors because I kind of want to find which one shows up the best. So if we're looking at that standard normal distribution, we want to find 3 critical values. The critical value that gives us 0.1 in the tail, critical value that gives us 0.05, critical value that gives us 0.01. And we want it in the right tail, right? Because we're dealing with a right-tailed test. So I automatically know all my critical values should be what? Positive, it's a right-tailed test, right? Because I'm dealing with the right side of this standard normal distribution, which I know the center of it is 0. Right? So I can use that standard normal table, look up the area that I want in the tail, which is alpha, right? 0.1 for this first one. The problem is, if I look up 0.1, what am I going to find? Remember, the table is looking at the area in the left tail. So if I look up 0.1, I'm going to find this exact same value, but negative. So I can look up alpha and just remember it's a right-tailed test. They have to be positive values. Or I could look up the area to the left of this value, which wouldn't be 0.1. It would be, area to the left would be, the area to the right is 0.1. The area to the left has to be 0.9. The area under the curve is 1, right? Wasn't a trick question. So we can do that either way. Either way will give us the right answer. So we could just look up alpha of 0.1. Looks like it's in between these two. So negative 1.28 and negative 1.29. Well, it's a right-tailed test. So if we just look up alpha, we have to remember it's that value but positive, so 1.29. Or we could look up the area to the left of that critical value, which we said was 0.9. So in between these two, so 1.2, in between 1.28 and 1.29, use the higher of the two, 1.29. Or I can go to my t-table and kind of cheat and say, I want 0.1 in my tail, go down to the very last row, 1.282, right? We need to be a little more specific if we use that, okay? So once I have that, I'll go back to here, and I've got approximately 1.29, right? Right-tailed test, so my rejection region's over here. I would use the exact same process to look up the other two and just have different alpha values, right? So if I go ahead and do that, instead of like walking through each one individually, since we already worked through one, it's the same process to find the other two. So I've got my rejection regions, and just to kind of remind myself, here was 10% level, 5% level, 1% significance level. Okay. What was my test statistic? It was like 1.09 or 1.1. So if I plot my test statistic, right, 1.10, I think it was. So this was my test or Z statistic, right? It's not quite in that rejection region, right? So same kind of, deal with the p-value approach. We said we couldn't reject, we failed to reject it at all the kind of usual significance levels. But notice, I mean, 1.1 is kind of close, getting closer to this cutoff. If I instead increase to alpha to 0.15, my critical value for that is probably somewhere over here. In fact, I could actually look that up. So if I wanted the critical value, that gave me 0.15 in that tail. So I'll go to 0.15 in between these. So negative 1.03 and 4. So negative 1.04. But I have a right-tailed test, so positive 1.04. Now when I draw that critical value, 1.04, right, would be actually to the left, and we can see there, now with our test statistic, we could reject with 85% confidence or 15% significance, okay? So both approaches lead us to the same decision, right? Any questions on that? So I think what I'm going to do is, I think we have one more problem to work through. Okay. So make sure. So we got our test statistic, walked through the p-value, made our rejection decision. I just want to make sure I didn't kind of forget anything there. Okay. All right. What if we go back to that survey example and want to test for whether or not there were different views between these 2 years? Now, confidence intervals and hypothesis testing are kind of similar, right? And so hopefully by the time we work through this example, I'm going to show you something that hopefully kind of connects the two, but shows maybe why one is useful in certain situations. So when we build a confidence interval for this, what did we say was possible, right? There were some negative values in our confidence interval and some positive values. Also, the value of 0 was in our, so if we do a hypothesis test and we test for whether or not these two proportions are different than each other, or we're testing for whether or not the difference is anything other than 0, so we assume it is 0. Well, if the confidence interval said 0 was one of the possible answers, we should be failing to reject it here, right? Because if we're testing for whether or not these views change between 2011 and 2010, what we're really saying when we said, have they changed, is that proportion in 2011 not equal to that proportion in 2010? Which, if we rearrange that, we're just saying, is the difference between 2011 and 2010 any value other than 0, right? Or not equal to 0? So that's what we want to test for. So, right, that's going to be our alternative hypothesis. We assume the opposite is true, which is that that's equal to 0, right? And here I'm just saying that would be the exact same thing. Okay? So we've got a two-tailed test here, but really what we're saying is just, is that difference anything other than 0? We'll assume the opposite is true, in fact, that difference is equal to 0, right? Well, our confidence interval told us, yeah, 0 could be one of the possible values, so we shouldn't reject this because this could be the true population difference. Right? So let's work through though and kind of and prove that to ourselves. Right? So, well, first of all, we have this two-tailed test. We know that we're looking for, we have sample proportions from both years. We've assumed that it's equal to 0, so they should be centered around that, right? We actually found, what, 0.84 and 0.82. So the sample difference we found, 0.02. Now for a two-tailed test, the area to the right of this isn't going to be my p-value. What else do I have to do? If the true difference was 0, and this is the sample evidence I found, it was equally as likely for me to see that same, something that far away from the assumed true difference, but on the other side. So this was the idea that once I look up this area, I need to multiply it by 2 to get my total p-value. Well, you can't really get that just from a normal distribution, so I need to turn this in to a standard normal distribution, right? And get my z statistic here. Once I find this area, I know I have the exact same probability of seeing something on the other side that would have went against my null, right? And so once I find this area, I'll multiply by 2, okay? So we go to our new test statistic equation. And I think here I have the critical values again, but we'll talk about this in a second. So if I'm trying to find that test statistic, right? Oops. I've got my new test statistic equation. I'll find p bar first, so I plug in 0.84 and 0.82, 607 and 600. I mean, this is just a matter of plugging those values in, making sure you can get that entered into your calculator correctly. That step shouldn't be tough. We get about 0.83, right? We then look at that test statistic equation, plug in 0.83 for p bar, plug in our sample sizes, plug in our two sample proportions. The assumed true difference was 0. We'll get a z-score of about 0.925, okay? So that's our z statistic, right, or our test statistic. We found a sample difference that was 0.9 standard deviations away from the assumed true difference of 0, okay? So we can think about where our test statistic would be. We found that our z statistic, or our test statistic, was 0.9, was it 2 something? 925, so if I round to the second decimal, 0.93. So I want to find the area to the right of that, right? Now, I know that if this is a symmetric distribution, instead of looking up 0.93, what might be something that's easier to do? Because if I look up 0.93, it's going to tell me the area to the left of 0.93. I'm going to then have to subtract it from 1. What's another way I could do this? I could look up negative 0.93. Remember, we said the reason why there's two tails is because it was equally as likely for me to see something that was just as far away from that assumed true value, but below it, Which remember, the z statistic is still a z-value. It still represents the number of standard deviations away from that assumed true mean. So really on the other side, we're thinking about that value but negative. So either way I want to do it. I could look up 0.93. The table gives me the area to the left. I then subtract it from 1. Kind of looks similar to what we did with the right tail test. Or I could look up negative 0.93. I think, personally, it's a little bit easier to look up that negative value of 0.93 since I know that's going to be the same area on both sides of my tail for a two-tailed test. So here's the 3-column, negative 0.93, 0.1762. Okay. So this area, 0.1762. This area is 0.1762. I can add them up, or if I found one of them, I can think about how do I get the total, just multiply it by 2, right? So for a two-tailed test, once you find the area in one of your tails, just multiply it by 2 to get your total p-value, okay? So here, well, the p-value would be 0.3524. See if I did mental math there correctly. Okay. So it's a pretty high p-value, right? I mean, can I reject it any of our conventional levels? Well, we only reject if the p-value is less than alpha. My alphas will be 0.1, 0.05, and 0.01. Is this going to be less than any of them? No. I mean, I can write it, you can write it out and say, maybe this is a good way to do it. So here's p-value, here's my alpha. My p-value is always going to be the same. Is 0.35 less than 0.01? No, so I fail to reject. Is it less than 0.05? No, so I fail to reject. Is it less than 0.35? No, so I fail to reject. Right? So we have another one, kind of another example where we can't really say anything with any decent level of confidence. In fact, this is worse than the presidential election one, right? I mean, this is 0.35. I couldn't even really say that with, 65% confidence? Right? So we failed to reject the null here at all levels. Now notice, I mean, it wouldn't really make a big difference here because the p-value is so large. But let's say instead we had found some different sample evidence and I end up with a p-value that's like, or I end up with an area in the tail that's, let's say 0.07. If I forget to multiply by 2 because it's a two-tailed test, I'll think that I could reject at that 10% significance level. But in fact, once I multiply that by 2, 0.14, well, now I would fail to reject, right? So if I forget to do that last step to find my p-value for a two-tailed test, I can end up with different rejection decisions, okay? So maybe you can kind of notice here, if I'm multiplying that area by 2, if I had set this up as a right-tailed test, well, then I could start to make some rejection decisions. So whenever I'm having a two-tailed test, it actually makes it even harder for you to be able to reject the null, right? Any questions on anything up here, or I said, or okay with that? Okay, I really wanted to kind of get through that. I'll come back to this example on Monday. We could find the critical values and kind of plot our test statistic against that. It's going to be very similar to what we did with the first example. But I wanted to try to go through something up here on the board that I think kind of connects that idea. Remember, we failed to reject oh, sorry. That's what I want to connect. So we just failed to reject at all 3 levels, right? Well, what was the assumption? The assumption was that the true difference was equal to 0. Well, we said we should fail to reject that because based off our confidence interval said for the same number, same example, said that 0 could be one of the possible differences. So if we think about what we're doing with hypothesis testing, so what we did there was say, is that true difference 0? We found evidence over here that failed to reject it, right? But what we could do is say, look, even though the sample evidence I found was 0.02, that was the difference that we had found, I failed to reject 0 as a possible value. Well, what if I use that same sample evidence and tried to say, well, what about 0.01? Well, that's even closer. So if I fail to reject that as a true difference, I'll definitely fail to reject this. I could start to test for all these different values, right? These assumed true differences. Sorry, that assumed true differences. You almost think about the sample difference. And I could say, okay, I failed to reject 0. I failed to reject -0.1. I failed to reject -0.2. And you could start doing a hypothesis test for every single possible value. What's going to end up being true is, based off that sample evidence I found, the values for which I'll be able to reject the null will only be the values that are past what we would have found if we built a confidence interval, especially for explicitly for a two-tailed test, right? Because we have kind of two tails there. So we could do a hypothesis test for every single value in this range. We're going to fail to reject until we get to values that would have been outside of that confidence interval range. So why do we do hypothesis testing? Why am I going to test against one value when I could just do this confidence interval where I can essentially like test against all these values all at once, right? Because when we just tested against 0, all I could say was, based off the sample evidence I found, I failed to reject 0 as a possible true population difference. Well, then I had to do a whole nother test to be able to say that I failed to reject -0.1. Whereas if I build my confidence interval, I can say, well, yeah, with 99% confidence, I can tell you, like, I'm saying all these could be possible. I would fail to reject every single one of these as the assumed true difference. So why do the hypothesis testing for just one number? Well, if we went through this hypothesis test, if I think about my p-value is the probability that I saw this sample evidence that was this far away from the assumed true value or anything even further. Well, if I start to test against different values, right, now my distribution is going to look something like this. That p-value starts to change, right? And so I'm going to have a different p-value for every single one of these values that I test against. And that p-value really lets me start to say, well, yeah, I can't tell you that -0.03 isn't the true population difference. I can't tell you that 0.07 isn't the true population difference. But with certain levels of confidence, some of these values are more likely to be the true difference than others, right? Because based off the sample evidence I found, these values are more likely to be the true difference than these values. And how much more likely? I could start to compare the p-values, right? Because the p-value tells me the probability or how likely it was that I would see any of these values based off the sample evidence I found, okay? Hopefully that kind of helps sort of, I don't know, just another way to think about this hypothesis testing connected to confidence intervals. Any questions on anything there? Where are we at with time here? Okay, one thing I wanted to say, I'm gonna put a quiz up today, but it's like another survey. I basically just get on and get it done and you'll get some points. Kind of lets me think about what I'll review and what I'll go over next week. So try to be thoughtful kind of going through and responding to the answers. Also, if you're watching the YouTube video ever, I realized the other day I posted one and it had an audio issue like the last 30 seconds, so it didn't really matter. But it was where my voice went robotic again. If it ever happens during the Zoom, let me know. But also, I think sometimes when I upload the file, because when I view it on my computer, it was fine. And then when I uploaded it, the last 30 seconds got corrupted or something. So if you're ever watching those and something like that happens, please let me know and I'll try to kind of splice the video and get it re-uploaded so that the audio issues are fixed. Okay? All right. Have a good weekend, and I will see you guys on